All right, it's 7 o'clock. Let's get going. Thanks for joining us tonight, everybody. Really appreciate you showing up tonight and learning about image processing in the narrowband spectrum with PixInsight with me. My name is Frank Kane. I'm the president of the Central Florida Astronomical Society. And if you're watching this video after the fact and you're not currently a member, you should be. Go over to cfas.org to learn more about our membership plans and be part of our community here around the Orlando region on astronomy and all things astronomy related. And I do want this to be an interactive session, so there's, only there's enough people here that we can get away with just talking to each other. So feel free to unmute yourselves, ask questions interactively. If you have anything you want to know more about, just holler, and that is totally okay. You don't have to wait to the end to answer your questions or anything like that. So let's dive in. So I want to start with kind of some background on what narrowband imaging is all about before we actually get into the processing, because I know we have some beginners here that might not know how to set up the equipment or why we're doing what we're doing or what we're really doing when we're processing narrowband images. So let's start with the basics before we actually dive into the live demo with PixInsight. And again, if there's anything you want more detail on, just holler and I'll try to dive into more information for you. So what is narrowband imaging after all? So basically, we're imaging through three different filters when we do narrowband imaging. So instead of doing these red, green, and blue filters that we can combine later into an RGB color image, that's just simulating what the eyes see. Your eyes have different cones for red, green, and blue. So to simulate what you would see with your eyeballs, if you had bionic vision and you could actually see these faint nebulas in the ether, that's kind of simulating what you would see with your eyeballs. But narrowband's a little bit different. What we're doing is targeting the emission lines of specific wavelengths associated with ionized elements of radiation. So we're specifically looking at what wavelengths get emitted when a star excites the hydrogen molecules of a cloud of gas in space, and what wavelength is emitted when sulfur elements get ionized by the light of a star, or oxygen, right? So we call those different spectrum lines hydrogen alpha, sulfur 2, and oxygen 3. And we abbreviate those as HA, S2, and O3. So the trick of narrowband imaging is that we simply have these really narrow filters that only let through the light that come from those specific ionized radiation from those elements that are lit up by some star behind them from an emission nebula or planetary nebula or what it is. And this is a nice trick for a few reasons that we'll get into shortly. But fundamentally, we're not filtering for red, green, and blue. We're filtering for the emissions from these specific emissions from these ionized elements that are being excited by the radiation of a star somewhere. So I said all that already. But the nice side effect of all that is that it blocks a lot of the light pollution and moonlight that's associated with your imaging. So if you're imaging from a light polluted area where you have a lot of night lights around or even moonlight, this can punch through a lot of that because we're only letting through very narrow slices of energy from the night sky that are associated with known emissions from these astronomical objects. So by doing so, we can filter out a lot of the light pollution and a lot of the moonlight that you would normally have. So even if you're in the middle of Orlando or the middle of Los Angeles, you can still get really beautiful long exposure astrophotography by using narrowband techniques. However, at the end of the day, your eyes still see in RGB. You have RGB cones in your eyeballs, right? So we have to map these wavelengths to visible color somehow. There's many ways of doing that, and that's where it's kind of the art comes in for narrowband imaging. Now, there's what we call the Hubble palette, which is what we usually go for. It's kind of what people have learned to expect from looking at all these processed images from the Hubble Space Telescope over time. The Hubble palette is simply, we take the sulfur 2 ionized emission radiation, and we map that to red. Hydrogen alpha, we map that to green, and oxygen, O3, we map that to blue. And by doing so, we get kind of these cool gold tones for the bulk of the nebula, and the oxygen emissions kind of pop out in the blue, and it just looks nice. But it's more than just looking nice. It's actually conveying scientific information as well. So by looking at the colors in a narrowband image, you can actually say something about what the chemical composition of that nebula might be. We can look at the blue and say, oh, that's ionized oxygen there. We can look at the gold and say, oh, there's a lot of sulfur and hydrogen going on there as well. So it's not just pretty pictures, although it can be. Like, it is possible to do artistic representations with this data, but if you just do this straight up mapping, which is what we're going to do tonight, you can actually infer some scientific information about this image as well. Tonight, we're going to be playing with the Pelican Nebula, only because it's the most recent one that I've done myself. So we're going to try to recreate this image here from scratch and see how it works. And I think you'll see that it's not really as complicated as you might think. However, narrowband imaging does come with some challenges that are unique to narrowband. First of all, because we're blocking out a lot of that light, we have these very narrow filters that only let through a little bit of radiation, right? That means that we need longer exposures to capture any meaningful information on that data. So while with a RGB wideband image that's just shooting natural color, you might be able to get away with like 30-second exposures or 60-second exposures. That's kind of pushing it for narrowband. So because of those really tight filters, we have to expose longer to get a signal through them. And that means that you're looking at usually more like 5-minute exposures for every subframe. That means that you need really good guiding or really good tracking or both to really pull that off, because you need to be able to do a sub exposure for 5 minutes without things getting all streaky and weird, right? So that means you need a good mount at the end of the day, or at least a good auto guiding system. I hate guiding. I'll get to that later. So I just rely on tracking myself, but more on that soon. The other issue is that most objects out there are dominated by hydrogen emissions. Most of the universe is hydrogen, like almost all of it is hydrogen, right? That means that you have to level these channels very carefully, because in the real world, you're not going to have a lot of sulfur. You're not going to have a lot of oxygen. And unless you do things to kind of balance those out, you're just going to end up with this green image because hydrogen is mapped to green. So green is ugly, right? People don't like green, at least in astronomy images. So we need to do a little bit of careful work there to level those images that are coming in from each channel of narrowband before we actually move forward. It's not that hard to do, though. I'll show you how to do it. And you can get artsy. Like I said, you don't have to do the Hubble palette. For some objects, hydrogen, oxygen, oxygen might be appropriate. If there's not a lot of sulfur there to begin with, that looks pretty good too. There's also algorithms for what we call synthetic RGB. So it's actually possible to recreate what this thing might look like in the visible spectrum just based on these narrowband signals. And we'll show you how to do that as well. But whatever you can dream up as well. There's all sorts of different mathematical combinations of mapping these narrowband emissions to RGB channels that look cool. And some people just want it to look cool, and that's fine. It's all about sparking the imagination. Another problem with narrowband is that the stars can be problematic. So if you look at some old school Hubble images, you'll notice that the stars look magenta, and that's because they didn't do anything to fix that. Like just naturally, stars end up looking magenta in SHO. And well, you could live with that, but it's kind of distracting if you ask me. There are a bunch of different ways to deal with that problem, and we're going to show you a few of them here tonight. One is to just filter the magenta color out. There are processes for doing that. You can just invert the image, apply a process called SCNR, which gets rid of green in the image, and then invert it back. That's one way to do it. Pretty easy. Some people actually take some separate RGB exposures through RGB filters just for the stars. And then they'll subtract out all the stars from their narrowband image and then add in the RGB stars from their RGB image. And you don't need a whole lot of time to do that. Maybe 20 minutes on each channel for RGB is good enough for that. So that's a pretty popular way of doing it. Or you can do it the way that I do it, which is to cheat, and I'll show you that tonight. So it is possible to process these stars in a way using just narrowband data that looks natural, and I'll show you how that works. A lot of people want to know how the gear works for all this stuff. So if you are new, what equipment do you need? Well, obviously you need a telescope. Personally, I use a Skywatcher 190MN. That's a Maksutov Newtonian design. It offers you don't hear about that too much. It's not a very popular design of telescope, but I love it. Because A, it's relatively inexpensive. B, it has a lot of aperture, 190 millimeters, in my case, to be precise, and more aperture is still better, even when it comes to astrophotography. And C, it's corrected. So there's a correction plate on the front of this telescope that flattens the field for me, which is important for astrophotography. So it is important to have flattened optics when you're doing astrophotography. You don't want to have stars that are like chromatically aberration or like smeared out or distorted at the edge of the frame, right? But the Maksutov Newtonian design has that built in. A more common choice would be like a refractor with a corrector at the end of the chain. Then that works too. But whatever you do, just make sure you have some sort of field flattening in place. Personally, my system is a focal length of f5.3, and that ends up giving me a field of view of around 1.7 degrees. So between 1 and 2 degrees is kind of a sweet spot of capturing most of the really popular narrowband objects that are out there. Some of them are much bigger than that, but it's only a handful of them. So, you can get most of the really cool stuff with around 1 to 2 degrees field of view. And like I said, you need to have a good mount. So you do need to do longer exposures for narrowband imaging because, they are narrower filters. They take more time to collect light through them. So you want something good, or at least a good auto guiding system. Personally, I use a Paramount Mighty mount from Software Bisque, which is a pretty high-end mount, sells for around $5,000 or $6,000. And with that, I can actually run unguided for 5-minute exposures and get away with it, usually, sort of, kind of. It's not perfect, but there is some variation also from mount to mount that, sometimes you get lucky, sometimes you don't, and how well they work. But I find guiding to be a pain in the butt. And one thing that you learn very quickly is that you need a lot of exposure time for narrowband images to look good. We're talking like 20 plus hours typically. So unless you don't like sleep, it's very beneficial to have a system that lets you image unattended while you're sleeping at night. And I find that guiding requires a lot of babysitting. There's just too many things that can go wrong. So if you can avoid guiding and just rely on a really solid tracking system, that will make your life a whole lot simpler. Also, obviously, you need a camera and filters. Personally, I'm using a ASI 2600 Pro camera, which is a cooled professional level camera-ish from ZWO. And you also need filters on top of that for hydrogen alpha, oxygen 3, and sulfur 2. And to automatically switch between those filters, you will furthermore need a filter wheel to automatically switch between those as you image through those different wavelengths. Or an alternative would be to use a color camera with what they call a duo narrowband filter. So there are filters out there that are built to only let through those emission lines for sulfur, hydrogen, and oxygen. And with that, you can just process that like you would pretty much like an RGB image. Or you could separate those out into what their narrowband equivalents would be and use the processes I'm going to talk to you about tonight. However, tonight we're going to be talking about using mono images, where we actually have explicit imaging runs for hydrogen alpha, oxygen 3, and sulfur 2, and we're going to combine those together in the processing stage. And nice to have automation software. Again, if you can run this stuff at night while you're asleep, all the better. And automation software is necessary to do that. Personally, I'm using a little mini PC in my observatory. It's running the Sky X because I'm using a software BISC mount, so I'm kind of tied into the software BISC software ecosystem there. And that furthermore leads me toward an application called CCD Autopilot for automating it. Again, that's just a software application from a third party that automates the Sky X over time and lets you plan out your sessions overnight. Now, if you're not using a software BISC mount, there are much more popular options out there, like ASI Air is a very popular option, Voyager, Nina, there's other stuff out there as well. They all work. It's also very nice to have a motorized focuser in place on your system as well, because as you're imaging throughout the night, unless you have parfocal filters, which usually you do, but even if you do have those parfocal filters, as the night goes on, focus is going to change just due to changes in the atmosphere. So the ability to automatically focus your system remotely is very, very much useful. Also, you need stuff for cable management and control. You can see that blue box on the top of my optical tube there. That's a Pegasus Ultimate Power Box 2 there. And its job is to take basically a couple of lines that I'm running through the mount just for power and USB and distributing that to all the other stuff that's on my optical tube, like the camera and the filter wheel and the DO controller. So it offers a place on the tube itself to plug all that stuff in, so I don't have to worry about all these cables getting caught up in the middle of the night unexpectedly, which always happens, right? Also, there's a weather sensor attached to this system as well. So if it unexpectedly starts raining, it can automatically close up the system, which comes in handy and lets you sleep well at night. And even better, if you have a robotic observatory like I do, that further makes life simpler for setting up because you can just leave stuff polar aligned all year long and not have to mess with it at all. So I can actually image from my office whenever there's a clear night and not even go outside, which you might consider a plus or a minus, depending on how much you like going outside in Florida. How it all connects. I know we had some questions earlier about how you put all this stuff together. This is just a picture that comes from the ZWO website. Basically, it's pretty easy. Usually when you buy one of these cameras and one of these filter wheels, they come with a variety of hardware that's made to let them connect to each other and to connect to most popular telescopes. In my case, you would just screw that ASI 2600 Pro directly to the ZWO filter wheel. And then that filter wheel in turn has a set of adapters that can be used to actually mate that to the eyepiece holder of your telescope. So it's usually pretty easy to do. Worst case, you might have to buy some custom adapter, but usually you don't. It always is a good idea, however, to at least get a filter wheel and a camera from the same manufacturer so you can make sure that they play nice with each other. There are considerations here for, back focus distances and things like that. I'm not going to get into that now, but usually it works out. The other thing you need to do is plan out the evening ahead of time. So you need to find a target that's going to be up in the night sky for most of the night sky and well positioned, and also not too close to the moon if the moon is out. For me, I use an application called CCD Navigator for that purpose. It leaves me sort of this menu that you see here of what's up tonight, what's its elevation throughout the night, how close is it to the moon. That's what this graph is showing you here. And ideally, like right now, the Hubble Nebula would be a really good target because you can see that blue curve there. It's showing me that in the middle of the night, that's going to be reaching its zenith on the sky up at 60 degrees elevation. That's pretty good. and it's also pretty far away from the moon. So in this particular example, this is showing that the Hubble Nebula would be a good choice for a narrowband target. Also, you want to make sure you check the weather, of course. I don't bother imaging if there's any chance of rain overnight or cloudiness. So I'm pretty picky about the weather. You don't have to be, but given that you're aiming for like 20 plus hours of total exposure time, a night that's only going to give you 1 or 2 hours might not be worth dealing with, right? So you want to kind of hold out for those better nights if you can. There's a lot of online resources for that, like Astrospheric, Clear Outside. Windy has some good tools for that. And also just the official government forecast from weather.gov can be useful as well. Also, before you get started with your imaging, you have to make sure you have your calibration frames in place. And if you're not familiar with those, I'll just briefly review what those are. So you will need at least dark frames. These are basically a set of images that you take from your camera while it's at the same cooling temperature that you're going to be shooting from throughout the night. And it's going to be matching the exposure times you plan to take as well. So I know that I'm going to be taking 5-minute exposures, that's 300 seconds. So I'm going to have a set of dark frames that I took ahead of time, about 20 of them, that were made at 300 seconds and also at -5 degrees centigrade on the camera, because that's what I shoot at in real life. Now, by taking those dark frames, which is just made by taking them at night with the lens cap on the telescope, that gives me sort of a picture of what the defects on the camera are that I need to correct for. So there's always going to be hot pixels on your camera. There might be other like various noise patterns on there that you need to cancel out. Dark frames will capture that information and allow you to correct for that during your image processing. It's a very important step. Also, you need flat frames, and these are capturing basically unevenness of the lighting on your camera and also the impacts of dust particles on your optical train. It might be on the telescope, it might be on the camera, who knows? But the flat frames can also correct for that stuff as well, and that's important as well. Now, dark frames will last you for a while. I just take them like once or twice a year because your camera doesn't really change that much over time. But the dust bunnies on your telescope do change. And the light pattern on your camera does change if you move the camera at all, right? So it is important to have a new set of flat frames taken pretty much every night to make sure that you can cancel those out accurately. Now, to do those, there's a bunch of ways to do it. I have what's called a flat panel in my observatory that has this evenly produced field of light that it produces. I point the telescope at it, and it takes those flat frames based on that even field of light. Some other techniques are what we call the T-shirt method, where you can actually just point your telescope up at the sky at a clear point of the sky overhead, throw a T-shirt over it, and that will give you a good enough flat frame. Or you can just point it directly at the zenith of the sky during dusk or dawn. If the lighting condition is just right, you can capture that period of time where the exposure works out for you. In a pinch, that works as well. A flat panel, of course, is going to be the best way to go. And again, you need at least 20 for each set of those for things to sort of average out and work out. And I'll show you some examples of what that looks like. Now, again, the more frames you get, the better. So like I said, the best narrowband images are going to have 20-ish hours of exposure time. You can get decent images with like 5-ish if you have a really bright target. You'll get okay images with around 10 to 13, but the truly, truly awesome ones, you're looking at 20 hours. So we're looking at imaging over multiple nights here, right? And you need some dedication to do that. Now, you also need some strategy to pull this off. So again, you need to think about the impacts of moonlight and light pollution throughout the night. And you need to think about how you're going to be timing these exposures throughout the night. This stuff is like just as important as anything else that you do when you're imaging. So we know that hydrogen alpha is going to be the most resistant to light pollution because it's usually the strongest signal from these emission nebula targets. So you can get away with doing your hydrogen alpha earlier or later in the night when your object is lower in the sky, and maybe there's more light pollution to deal with because you know that hydrogen alpha signal is going to punch through that better. And you probably want to save your sulfur and oxygen data until your target is higher up in the sky, right? Because then there's going to be less light pollution to deal with. You'll get more signal to noise ratio, and you'll make better use of your exposure time for that. So typically you want to make sure your hydrogen alpha is done while your target is lower in the sky, and sulfur and oxygen when it's higher. And you want to ask yourself too, do I even need to take all of these different exposures? Do I even need sulfur too? There's a lot of objects out there that just don't have enough of it to be worth doing. So you want to do a little bit of research ahead of time before you do some narrowband imaging. You want to find out, how have other people taken really pretty images of this of this thing that I'm looking at? Do they have any sulfur too, right? So for a lot of planetary nebulas, for example, there's not a lot of sulfur. It's mostly hydrogen and oxygen. And you can get away with just doing hydrogen and oxygen and skipping sulfur altogether. So that'll save you a lot of time if you know that up front. And some objects don't even have oxygen in them. So like some of them are just mostly hydrogen. In that case, you might want a different strategy altogether where you just take RGB data and enhance that with hydrogen alpha data later on. And well, that would be the subject of another tutorial later on, maybe. All right, so you've taken these pile of images throughout the night. Now what? So this is going to be basically the process that we're following throughout this tutorial. We're going to start by pre-processing all of the images we took throughout the night using a process in PixInsight called weighted batch pre-processing. What that's going to do is apply all those calibration frames, the dark frames, the flat frames that we collected earlier, and use that to subtract out all those dust bunnies and vignetting and camera defects from our subframes right up front so that we have really clean data to work with and start from. It's also going to do the work of integrating those images as well. So I might have, 100 images of hydrogen alpha. I want to combine those into one image, right? And sort of use the power of that combination to get higher signal to noise ratio. So we'll do that integration as well for each channel for you automatically. This has all become really, really easy in PixInsight lately using weighted batch pre-processing. A few years ago, this would have taken half the night. After that, we're going to end up with these master frames of hydrogen alpha, sulfur 2, and oxygen 3 emission data from our target. First thing we're going to do is crop that down to the area of interest and make sure that we crop out any artifacts around the edges of the images. We're then going to do any gradient corrections that we might need to do to the image. So if your image was, close to the moon or like there was light pollution around it, often you'll end up with these sort of gradients of light across your image throughout the night. And correcting for that can really help make your image pop better. So there are AI tools for doing that, which we will use. Then you want to de-blur it. This is called deconvolution. This is different from sharpening. So a nice thing about astroimaging is that we end up with these point sources throughout the image from the stars, right? And we can use the information of how the light from those stars are spread out to kind of reconstruct what that image would have looked like if it weren't blurred at all. If our tracking was absolutely perfect, if our, what would it look like if there was no error whatsoever? We can mathematically correct for that now, which is really, really exciting. So even if your tracking isn't perfect and spot on, we can correct for that now using these de-blur tools and deconvolution tools. And you'll see the magic of that shortly. We also want to do a little bit of noise reduction potentially. So if you have any light pollution at all going on, you're going to have noise. So it's up to you how much you want to reduce that. That's a little bit of an artistic choice. But today's modern AI-based noise reduction tools are really, really good. And they're worth doing. We'll show you that as well. Then we need to balance those channels. Like I said, hydrogen alpha is going to be dominating pretty much every object that you have out there in the narrowband world. So we need to balance those with sulfur 2 and oxygen 3. That's where the linear fit process comes in. Now, there are scripts out there that kind of automate this for you and offer fancier ways of doing it, but linear fit isn't that hard, and it kind of shows you how it's really working and what's going on under the hood. So that's how we're going to do it tonight. After that, we're going to have these fully corrected and balanced sulfur, hydrogen, and oxygen master images. We need to combine them together into a color image that your eyes can interpret as color. That's where we're going to actually apply that SHO Hubble palette, and we'll use a tool called channel combination to do that. Once we've done that, as you'll see shortly, these unprocessed images they look weird, right? The actual light from the nebula itself is very, very dim compared to the light from the stars. So we need to manipulate those images to bring out that nebulosity from the background that's kind of hiding behind the stars. That's what we call image stretching or histogram optimization. So we'll show you how that works as well. And once we're back in the nonlinear domain there, that we stretch our image to make it all visible, we need to do something about the stars. So like I said, they tend to be magenta. You could leave them that way if you want to, but I don't want to. So I'm going to show you some techniques on making them look better. And once we're done with that, we'll do some final tweaks. We'll just play around with what we call curves to kind of like adjust the color balance and adjust the contrast, and maybe do some local contrast enhancement as well to make it look even better. Now, there is no one way to do this. So there are many, many tutorials out there. They all have their own way of doing it. What I'm going to show you is kind of the most straightforward way, assuming that you're a beginner. It's going to be the easiest way to understand, and it still produces some really good results. But there is a very, very deep rabbit hole you can go down with narrowband image processing. If you really want to get into the weeds of it, you can check out atom blocks tutorials, for example. There's all sorts of tips and tricks out there for making it even better. But what I'm going to show you tonight is going to get you 95% of the way there. And if you really want to chase after that final 5%, well, that's part of the fun of the hobby, and I invite you to do so. But we're not going to go to the point of diminishing returns tonight. I'm just going to show you how to get a really good looking image using some very straightforward techniques. But I want to also point out that there is no like recipe for this either. There's no like set of steps you can follow for every image. It varies from target to target. So you kind of need to think as you're doing this. And I'm going to try to talk you through that tonight. So at each step, as we're doing our image processing, we kind of need to ask ourselves, all right, what are the problems here that I need to solve? What's wrong with this image? What am I trying to fix in it? And then think about, well, okay, what tools can I use to fix that? So you kind of need to be critical as you go through it and really look out for images because it's the sooner you catch a problem, like my stars are bloated or the color balance doesn't look right or things look too green, whatever it is, you want to catch that early on because if you don't, you're going to find yourself using the undo button a whole lot to go back and start over. So you really need to be critical as you go at each step and kind of, change your approach as you go based on the challenges that you're facing. Now, we're not just using straight up PixInsight tonight, and very few people do. And I think, in Wes's tutorial, we saw some of the same tools being used. So I'm going to be using some add-ons to PixInsight that cost a little bit extra. That includes Blur Exterminator, Noise Exterminator, and Star Exterminator, all from RC Astro. And you may say, oh, I don't want to spend more money, but God, come on, you spent so much money on gear already. What's another 80 bucks? I mean, it's well worth it and just as important as any gear that you have for making your images look good. So these are all very good investments, I assure you. We're also going to be using a tool called Graxpert, which is an AI-powered gradient removal tool. PixInsight does have some improving gradient removal tools of its own built in. They're still not as good as Graxpert, though, in my opinion. I've tried some of them, and Graxpert just works, so I'm still going to use that tonight. Again, Blur Exterminator, Noise Exterminator, Star Exterminator are all available from rc-astro.com. Highly recommend using them. And Graxpert can be got from graxpert.com. So before we dive into actually processing this data, I want to take a moment for any questions you might have, and I will stop blathering. Just feel free to take yourself off of mute if so, while I fuddle-duddle with Zoom here. All right, so I think I successfully stopped PowerPoint. Clear as mud for everyone?
What's the bandwidth of these filters? How wide are they?
It depends how much money you want to pay. So I think the ones I'm using are 7 nanometers, but you can go down to 3. And the narrower, the better, but also the narrower, the more exposure time you're going to need to get a signal, right? So it's a trade-off. If you have like a 3 nanometer band, then you're going to cut out even more light pollution and your images are going to look that much better. But they're going to cost like, probably around $100 extra per filter. So it does add up. I'm using 7 nanometer filters myself. So you be the judge. Again, it's one of those cases where you kind of get into this world of diminishing returns. So you can spend infinite money on this hobby to get that last 1% of quality out of it, right? And the bandwidth of those filters is one of those cases.
If you had to go big on one of them, go big on the OIII. The smaller the nanometer on that one, the better, since it's usually the weakest.
Yeah, good call. Yeah, you'll find that even on a moonless night, you're going to get a lot of noise on O3 just because it's such a dim signal on most targets. For some targets, sulfur too is also pretty dim, but hydrogen alpha, like that's always just going to punch through anything. So yeah, that might be one you might want to save on. All right, let's see if I can figure out how to share PixInsight here. All right, I think that worked. All right, so let's dive in. So like I said, I'm going to be processing some data from the Pelican Nebula tonight. So let's go ahead and show you how we would process that. Now, the first step is to pre-process that data. So we need to apply those calibration frames, the darks and lights, before we can actually do anything with the data, and then integrate it all together into these master frames from each filter. So let me just show you real quickly what these calibration frames look like. So for example, here's one of the hydrogen alpha calibration frames that came from this target. And first lesson of tonight is screen transfer function. So just a quick tour of PixInsight here. So I have some icons over here of some processes that I use pretty frequently. They're just kind of a shortcut. For all of these things, you can just go to the process menu, however, and find them up here. So I could go to all processes and go to screen transfer function and get to it that way as well. What screen transfer function does is kind of cheat. So it takes this image that was taken in a linear channel, in a linear format, and wow, that's hard to say. Delinearizes it. Yes, that's it. to actually make it stretched out and get those details in the background more visible. So if I hit this little radioactive icon here and I make sure that I have this image selected, it's going to stretch that image for me to make the details that are kind of buried in the noise pop out a little bit more. And you can see how that worked there. So here we can see that this flat frame, which was taken just by pointing my telescope and its camera at this uniform field of light, you can see that I've got these corners here of darkness. That's because the actual image circle from my telescope is not covering the entire sensor of my camera. And I'm okay with that. I've learned to live with that. But in a perfect world, that would not be the case, right? But it does mean that when I get my images, the data in these corners is going to be kind of suspect, and I might need to crop that out. We're also seeing these little donuts here, right? So what's that? So those are the impacts of what we call dust bunnies. So any dust particle on my telescope is going to show up as these sort of donut holes here. And again, if it's important to be able to subtract that out because I don't want these donut holes in my final image of my picture of the Pelican Nebula. So the flat frame will subtract out the effects of this vignetting as best as it can, and also these donut holes from dust bunnies. So that's what flats are all about. We're also going to be applying dark frames. See if I can find those real quick. So again, you can just have this library of dark frames that you kind of hang on to for the year, as opposed to flat frames, which you really need to take every night. Where did I tuck mine away? There's some. Sure, we're using 300-second flats here. Again, I'm matching that to the temperature and exposure time that I'm using. And again, if I hit the radioactive button here, I can pull that out. And you can see what we're getting here is kind of this pattern of all these hot pixels, or hotter than usual pixels, on my camera. So this is actually mapping out the defects or the inconsistencies on my ASI 2600mm camera. And it can subtract that out as we're processing these frames to make it appear as though those defects didn't exist. So that's what dark frames are all about. Now to actually apply that, we're going to go to the process menu, and under all processes, wait, no, it's not under processes, it's under script, batch processing, weighted batch pre-processing. All right. And that's going to bring up this big old dialog box eventually, once my hard drive spins up. And that looks like this. So you can see here, you can add bias frames. If you were using like a CCD camera, that might be useful, but for modern CMOS cameras, which is probably what you're going to buy today, you usually don't need bias. Darks are enough. And you can see here, I've already added in these master dark frames that I've created ahead of time in my dark library. These are all previously integrated dark frames for various exposure lengths. They're all for -5 degrees Celsius because that's what I shoot at. And you can see I have this library of 1 second, 5 second, 10 seconds, 60 seconds, 120 second, and 300 second exposures. Tonight, we're just going to be using the 300 second exposures because I'm doing narrowband, and that's what I expose at personally for narrowband. To add more, you could clear those out, and that would reveal one of these buttons down here. You can just hit plus darks if you wanted to add more dark frames that you collected already. Same thing with flats. What I would do is just hit the plus flats button down here. And from there, I could navigate to wherever I save those. For example, session 1, calibration file. So these are all the flat frames that I collected for that evening. Now, this is a good time to mention that I'm actually integrating 3 different nights worth of data here. Like I said, you need to get a whole lot of integration time, and that usually means multiple nights. And that might mean multiple sets of flat frames if your camera moved during that time. So in this case, I'm actually going to be integrating data that I took 2 years ago from data that I took last month. And obviously my flats have changed during that time. So one way of dealing with that is by using what we call grouping keywords. So over here, you can see that I've checked on the grouping keywords checkbox here and put on a keyword of session. So the trick here is that because I renamed the folders that my flats and lights are in with session_1, session_2, and session_3, these will all correspond to different nights that I took the data on. So basically here, session 1, 2022, 0806, those are the flat frames, the calibration frames that I took that night. The actual data, the hydrogen, oxygen, and sulfur data that I took is in that folder as well. And since they both start with session 1, those are going to get grouped together automatically by PixInsight. So it's going to know to match those flat frames to those light frames when it's doing the calibration. Similarly for the second and third nights as well. So it's a little bit tricky to wrap your head around how grouping keywords works at first, but it's really just that simple. just rename the folders that your data are in consistently, and you can put that prefix that it looks for ahead of that in your grouping keywords. Now, I'm not going to make you sit through this. The next step would be to add all of your light frames. These are the ones that are actually your hydrogen, oxygen, and sulfur data. So for example, here, session 3, IC 5071, that's where I actually saved all of my data from that night. I would just select all of that and add it in here. And once I'm done, there's a couple of things you need to do. First of all, when you're looking at the weighting formula parameters, when you have the lights tab set there, you want to make sure you check that. We're imaging a nebula here, so I want to make sure that's set to nebula. Obviously, if it was something else, I would set it to something else, but very important to get the weighting right there so it knows what to prioritize when it's doing the calibration. I'm not going to get into the other stuff here because I don't want to be here all night, but generally speaking, you can more or less just leave these on default for the most part. The other thing you need to set, though, is the output directory. You need to select a folder on your hard drive where you want to put all the processed files and intermediate files and the final master files when you're done. So you just hit the folder icon there, select the folder that you want that to go into, and that's it. Once you're done, just hit the run button, and that will run for literally most of the day. This is the longest part, but fortunately, it's all automated. Now, I'm not going to make you sit through that because it would take hours and hours and hours. Instead, I'm going to kind of act like I'm in a cooking show where I put the turkey in the oven ahead of time, and I'm going to pull it out now fully cooked. So if I go to that directory that I specified for the output, which was D Pelican 2024, the final master calibrated integrated frames are going to be in the master folder. And you can see here that saved all the integrated flat frames from all 3 of those sessions for all 3 of those filters, hydrogen, oxygen, and sulfur for each one of those 3 nights. And it's also, more importantly, giving me the integrated light frames here as well. So I'm interested in these 3, the Master Light HA, Master Light O3, and Master Light S2. So let's select those and open them up. All right. And again, if you have any questions as I go, just holler. There's enough of us here that we can get away with that. All right. So this doesn't look very exciting, does it? We just have a bunch of dots here. So again, that's the thing with astrophotography. There's this huge difference in brightness between these faint gases being lit up by faint stars in the background and the starlight surrounding them. So this is what we call a linear representation of the image data, where this is just straight up showing you what is being recorded on the camera. And the stars are so much brighter than the nebula that you can't even see the nebula. So we got to do something about that. We can't really know what we're doing there. I'm going to do a couple of things here. First of all, I'm going to rename this thing to something a little bit easier to deal with. So this is the sulfur 2 frame. And you can see that the default name that weighted batch preprocessor came up with is this huge thing, master light bin 162, 48, 41, blah, 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 right? That's too much to type. So I'm going to go ahead and click on that. I double clicked on that little side tab there. And by doing so, I can give it a new identifier. I'm going to call that S2, just to make life easier. All right. So now you can see that this is called S2, which is what I can refer to it later on. And now to actually see what's going on in this image, again, I'm going to use screen transfer function and click the radioactive button. What a difference, right? So now we're seeing some actual interesting image data here from the sulfur 2 filter that we took over those 3 nights. And we can kind of zoom in and get a feel again for what we're up against. So the data is pretty noisy, even over 3 nights. Sulfur 2 is pretty weak for this target. So there's some noise there to deal with. Also, the stars don't look too bad, but they are a little bit stretched and a little bit bloated. So I want to deal with that too, for sure. But on the whole, it looks pretty clean. Another thing to look at is the edges of the image. So you can kind of see, I'm not sure how well this is coming through across on Zoom, but there's definitely some artifacts here in the corner. Some of this is just due to things not aligning consistently throughout the night. Some of it's due to that vignetting that I showed you earlier, but either way, we're going to want to crop some of that out. So this part here is probably not something we can easily correct for. So sometimes the easiest thing to do is to just crop it out of the image entirely. And that's going to be the first step in our processing, actually. But first, let's take care of the other channels as well. So this one's O3. I'm going to rename that by double clicking on the sidebar there to O3. And click on the radioactive icon again. And like Wes was saying, O3 is actually pretty weak, but it's also going to be a good source of kind of visual interest in our final image because that's what's going to map to blue, right? So this is going to end up being a really pretty blue at the end of the day, but there's not a whole lot to work with here. And if we scroll in, we can see, yeah, we got a lot of noise to deal with there. Stars aren't too bad though. So that's the good news. So those 5-minute unguided exposures actually worked out. However, you can see there, we definitely need to crop out that area of the image there just because of rotation over these different nights that kind of made things not line up perfectly. So all you can really do about that is to crop it out, and we'll get there in a minute. Finally, let's take care of hydrogen. So double click on that. I'm going to rename that to HA, hydrogen alpha. And again, blow that out with the radioactive button. Now, I want to point out too that the underlying image data here is still linear. We haven't actually changed anything in the image itself yet. By applying the screen transfer function, we're only changing how it's displayed. We haven't actually modified the image in any way up to this point. We're just visualizing it differently. And this little green bar here is an indication of that. So that green bar means that we're actually applying this screen transfer function to it, that what we're seeing is not what's really in the image. So important to watch out for that. It's easy to get confused. Let's zoom in here. Again, hydrogen alpha is usually a lot cleaner. However, you can see that my tracking kind of sucked. So my stars are very oblong here. And a couple of years ago, I might have said, oh, that's terrible. I got to start over. I would have gone back and thrown out all the frames that were really poorly tracked. But again, with the magic of deconvolution and blur exterminator, I don't have to anymore. So I'll show you how that works shortly. All right, so we've got our hydrogen, oxygen, and sulfur master frames here. This is like straight out of pre-processing. First thing we want to do is crop them, like I said. So it looked like the messiest one was the oxygen 3. It had this kind of like big wedge here that looks bogus. And there's also a little bit over here from sulfur 2. So I know that at a minimum, I got to crop out a little bit there, right? But let's also think about the image composition while we're at it. So we got to think about what looks good at the end of the day, right? What we want to focus on in our image. There's a little bit of art here that we need to apply. So first of all, this whole thing looks upside down, right? So in the back of my head, I'm kind of thinking already, well, I want to flip this thing at least 90 degrees, maybe 180 degrees when I'm done, because it just looks like it's pointing down. And you never want an image that looks like it's pointing down. For visual interest, it should be pointing up. It should be like moving from left to right. You want to get some sort of motion that looks natural and, well, uplifting, if you will. So we're going to do that at the end, but I'm just kind of like keeping in the back of my head that at some point I want to flip this around. The other thing is that all this stuff out here, it's kind of ugly. It's kind of like smeary looking and I don't like it. So I don't want that in my final image. What I do want to focus on is this stuff in here. There's some really interesting stuff going on in this part of the image, right? So if I zoom in, there's actually some Herbig Harrow objects going on here. Like, look at the tip of this little tendril here. That's actually jets of material being spat out by a forming protostar. How cool is that? Like, you can actually see that from your backyard. That's amazing. So I want to focus on that. This is something I definitely want to highlight in my image. So at the end of the day, I'm thinking I want an image that's kind of cropped kind of like this, maybe a little bit more vertically, but this is the part that I want to focus on. There's also some interesting shock waves going on out here. There's more Herbig Harrow objects around here. So I have enough image resolution that I can get away with really cropping on just this part of the image. So let's do that. So I'm going to kind of adjust the scale of this image so that I have a little bit of this gray border around it to work with. And what I'm going to do is apply the dynamic crop process. Again, I just have these shortcuts here from PixInsight, but you could get there from the process menu as well. And once I do that, and you might have to hit the reset button here to actually apply it to the image that's selected, we're just going to drag these edges in. Now, quick note here about PixInsight's user interface. It is terrible. Terrible, terrible, terrible. It makes no sense whatsoever. So let's just get that out of the way right now. So this icon here, that thing that looks kind of like a target, that resets to the original default settings for the process that we're looking at. This gives you some various configuration options that you'll probably never need to look at, documentation links. What gets really weird are these ones here. So you're used to seeing like OK and cancel buttons in normal applications. There are no OK and cancel buttons in PixInsight. Instead, there's a check mark, which means to apply this process to the image that you have. There's an X that means to cancel what you're doing to the image. And then there's this weird triangle thing that we're going to talk about in a second. But first of all, let's get the cropping that we want. So like I said, I want to focus on this area. So I'm going to wait till I see that little indicator on top of that square there and drag this down a little bit. Actually, not that much, because there is some interesting formations going on right there. Now, as I'm doing this, I want to be careful not to cut any bright stars in half, right? So I want to be careful not to intersect a star with that crop line, because half a star looks kind of weird. So I'm also being careful about that. Now over here, I'm going to pull it in a lot more because again, I want to focus on kind of this central region here. There is some interesting stuff going on there, so I don't want to lose that, right? And let's pull in the bottom, maybe around there. Again, we're just kind of like artistically framing this thing. And again, I'm being careful not to bisect any stars in the process. And let's pull in the left as well. And you can see that I've also positioned the center to be kind of in the center of that main region there as well. This is where you want to apply like your composition knowledge. So sometimes the rule of thirds would come into play. In this case, I can't really think of a good way to apply that to this image, but if you can, anything you would use in conventional photography is fair game for astrophotography as well in terms of composition. All right, so I'm pretty happy with that framing. What I'm going to do, I need to apply that exact same crop to the other channels for things to align when I combine them all together into a color image. So that's where this little triangle comes in. I'm going to grab this triangle and drag it out to my desktop here. And what that does is create a copy of all these settings into what we call this process icon. And that will allow me to apply those same exact settings to my other filters as well. First, I need to apply this one though. So let's hit the check mark icon to apply that crop. And now I'm going to blow this out. I'm going to right click on that and say zoom to optimal fit. Okay. So I've cropped hydrogen alpha. Let's use this icon to kind of minimize that window. Tuck this away somewhere. Now I need to apply the same crop to the other channels. So for oxygen 3, the way I do that is I take that saved process and I just drag it onto it. All right. And that applies the same exact crop to that one. Right click that, zoom to optimal fit. Let's tuck that away as well. And finally, we'll do the same thing to sulfur 2. Drag it on there. Zoom it out a little bit, close it. All right, so now I'm done with cropping. I can close out this dynamic crop process, and I'm done with that process as well, but we'll leave it around. Why not? We'll let it live. All right, next thing we want to do is deal with, let me get my cheat sheet, but I think it's gradient correction. Yep. So, like I said, there can be inconsistent patterns of light pollution in your images, and we need to correct for that somehow. Let's start with hydrogen alpha. Now, with narrowband data, it's usually less of an issue. Like this is definitely a much bigger issue with full spectrum wideband photography, but it's still worth doing for narrowband as well. It's kind of hard to see if there are any actual gradients here. I don't see them, but you know, sometimes the algorithms can see things that you don't. Now I'm going to be using a third-party tool called Graxpert here to pull it off because it's easy and it just works. So to get to that, I'm going to go to Script. I think it's in Toolbox, Graxpert. And again, this is the third-party add-on that you need to pay for and install into PixInsight. And you could get into what all these knobs and dials mean, but I'm not going to. What I am going to do, why didn't that go away? Anyway, the HA window is currently selected, so I'm going to hit the check mark to apply that to my hydrogen alpha channel. And it'll take a little bit of time for it to run the first time, but usually it's pretty quick after that. All right, we're done. And I'm not sure how well you can see that on Zoom, but again, that's looking pretty good. You know, that's definitely an improvement. We have a little bit more contrast than we used to in this image, so that's cool. Let's do the same thing to the other ones. So let's close out hydrogen alpha, open up oxygen 3, and do the same thing. Script, Toolbox, Graxpert, and apply that as well. Now, some people will actually do the channel combination first and combine this all into a color RGB image and then apply this to the entire image at once. I just like to do it one channel at a time because I think it gives you a little bit more control and you can see what's going on. Let's do the same thing for sulfur. Script, Toolbox, Graxpert. Check mark. All right, so we've applied gradient correction to all 3 of our channels at this point. Cool. The next thing I want to do is do deconvolution. This needs to be done very early in your process for it to work properly. And this is going to be, again, sort of correcting for the tracking errors that happened throughout the night. So for hydrogen alpha, it was the worst. So again, if I zoom in here, you can see that my stars are not circles at all. They're these like really weird UFO shaped things. That's terrible. So I need to fix that somehow. Blur exterminator to the rescue. So again, this is the third-party process, but you can find it under process once it's installed, under Blur Exterminator. And I could get into what all these different values mean. They all have their applications, but I'm not going to go there tonight because we'd be here all night. So I'm just going to show you the easy way, which is to just use the defaults. So again, I'm making sure that hydrogen alpha is selected, and I'm just going to hit this square icon to actually apply that. Oh, the UI changed on us. So sometimes apply is a check mark, sometimes it's a square. There is some rhyme or reason to when they choose one or the other, but in this case, it's a square. So we're going to hit the square button to actually apply that Blur Exterminator process to our image. Off it goes, and magic will ensue. All right, and you can already see that looks better. So if I zoom in, look at that. My stars are perfectly round, they're tight. It's just absolute magic how it works. But it's not magic. It's all mathematical. Like, this is not doing anything to fake anything in your image. This is still real data. It's not fabricating anything like AI sharpening might do, right? So tools like Topaz denoise or Topaz, whatever they call it these days in Photoshop, that will often make up information that isn't really there. But we have not done that. With Blur Exterminator, it's doing something called deconvolution, which is a mathematically legit thing to do. It's just applying a correction based on that point spread function of the stars. And you can also see that we have a lot more detail than we had before on the nebula itself. So that Herbig-Haro object there, for example, looks a little bit tighter than it did before. So that's really cool. Let's again apply that to the other channels as well. So I'm going to select O3, hit that square again. And again, if you have any questions, just pipe in.
What kind of computer you got? And like how many cores and how fast is it?
Good question. It's actually pretty old. I've had this for about 5 years now. Let me see if I can actually pull up the specs for it here. It is a i7-9700K CPU with 32 gigs of RAM. I want to say it's 8 cores, but I'm not sure.
Okay.
But what's more important is the GPU, actually. So when you're doing all this AI processing, like with Blur Exterminator and Star Exterminator and Graxpert, if you set it up right, that can take advantage of your video card and your GPU. So I've got an NVIDIA 3090 on this system, I think it is. And it's really relying on that more than the CPU.
Makes
So,
sense.
yep. All right, so we've applied Blur Exterminator to the oxygen data here. Let's also do that for sulfur. And by the way, if I did not have this set up for the GPU acceleration, that would have taken about 10 times as long. Let's go ahead and apply that to sulfur. And we're done. All right, so at this point, we've cropped all of our individual frames there. We've done gradient correction, and we've also deconvolved them. We've corrected for any blur. So cool. Already things are looking a little bit better. Now, I want to show you how to save this as we go. So, if we were to lose power or something, that would make me sad. That would be a lot of work to redo. So at any point here, let's close that out. We can save our project. So we could say, save project, create a bundled project, just navigate to wherever you want to put it. After my hard drive wakes up, maybe I want to call it, I don't know, Pelican 2. And from there, you can just hit on OK. And by doing that, you can open up that project file later on and pick up where you left off. So that will save also the entire edit history on each one of these files. So if you were to quit this and come back to it later, you can still undo stuff and kind of go back and recreate your steps if you needed to. So if you don't want to risk losing your work, that's how you do that. All right. So like I said, the next thing we need to do is to try to balance these different channels to each other such that they look good when combined. So again, hydrogen alpha is just much, much stronger than the other channels. And if I were to just combine these together into a Hubble palette where sulfur is red, hydrogen is green, and oxygen is blue, it would just be a green image. And nobody likes a green image. You know, I mean, yeah, it looks like grass or whatever, but it just doesn't look right for things in space. So we're going to use a process called linear fit to correct for that. Now, I've seen multiple advices on how to do this properly. Some say you should fit on the strongest signal. Some say you should fit on the weakest signal. I believe the correct answer is to fit on the weakest signal, and often that will be oxygen. The other advantage that it has is that by kind of balancing everything on your oxygen frame there, it really pulls out that blue oxygen more in your final image. So just again, eyeballing it here, you can see that there's a lot more detail in sulfur and hydrogen than there is in oxygen. A more legitimate way of doing this would be to just mouse over the images and kind of take a look at this K value down here in the corner here. That's the actual pixel value as I move the cursor around. And you can see here for oxygen, it's like around 0.04 for the most part. Whereas, for example, in hydrogen, well, actually, it's not that much different, is it? That's interesting. It's pretty well balanced already. But it's still, 0.5 there, for example. It's still definitely stronger than oxygen. But that's one way to measure it. But sometimes it just comes down to which channel do I want to pull out the most. So let's go to linear fit. Usually the right answer is going to be oxygen, but sometimes you just want to experiment and see how choosing a different reference image affects your final image when you combine them together. So I've chosen oxygen 3 as the image that I want to use as a reference. I need to apply that to the other two. So we'll start by HA. To do that, again, PixInsight's UI is weird. The way I'm going to do that is not by clicking on the apply button, which you would imagine. I'm going to take the triangle icon and drag that onto the HA image there. All right, so that's balanced that. And we also need to apply that to S2. Again, drag the triangle onto the S2 image. All right, so what we've done here is basically balance these images such that their noise backgrounds are equivalent. And this will have the side effect of making our colors look nice and balanced, hopefully. And again, I'm not going to apply that to O3 because that is a reference image already. All righty then. So next step is RGB combine. This is called the channel combination process. Again, you can find that from the process menu. And to do this, I need to select which of these images I want to map to red, green, and blue. And since I'm going with the Hubble palette, I'm going to map. I'll click on that icon there and change red to sulfur 2. We're going to map green to hydrogen alpha. And we're going to map blue to oxygen. And in this case, I'm going to use the circle icon because, again, there's no consistency to PixInsight. That means I don't necessarily have to have anything selected that will automatically pull in those images as needed and apply this process globally. All right, what do we got? So again, this is in the linear domain, and you can see those magenta stars already. Let's go ahead and hit the radioactive icon to pull out the actual image there. Bam. Hey, we're getting somewhere, right? So again, note that that green line got added there, noting that what I'm seeing is not representative of the actual data, that I'm stretching that out to see what's in it. Let's go ahead and rename that from image 10 to SHO. Sulfur, hydrogen, oxygen. All right, we're getting somewhere. This is starting to look like something, right? So that's starting to look like a Hubble image. Pretty cool. Now let's, again, be critical of the problems that we're facing. So as I zoom in, I see two main problems. One is that the stars are pink, and I don't like that. Some people can live with that. I can't. So I want to fix that. Also, a little bit more noise than I would like. So let's go ahead and fix that first. Noise reduction is something you also want to do earlier on than later if you can. And for that, there is, again, a third-party tool called a noise exterminator that I can apply. Now, how much denoising to apply is a bit of an artistic choice. If you make it too high, if you apply too much denoising, it might end up looking a little bit plastic and unrealistic. Space is not completely black, so a little bit of noise makes it look a little bit more, easier to swallow, if you will. I've settled on 75% in this particular example, but you might want to experiment with that. So let's try 75% and see what happens. I'm going to hit the apply button in this case to actually apply that to my image. And we're done. And if I zoom in, I can see there's still a little bit of noise, but most of it's gone. And I actually like how that looks. If I wasn't satisfied, though, I could just go up to image and say undo and change the image and do it again. So it's always possible to go back in time and just try something over with slightly different settings. There's also like a history editor over here on the side as well that you can go into if you want to go even back even further. All right, so I'm happy with that. That's cool. New problem. So those magenta stars, what am I going to do about them? So I'll show you a few ways. One thing you can do is, again, just apply a filter to magenta. And there are scripts that will do this for you. However, kind of the basic way is to go to process and invert the image. And then I'm going to apply what's called SCNR, which is a green filter. Since I've inverted it, my magenta has become green. And now I need to invert it back. And sometimes this works well enough. But in this case, it didn't. So now instead of magenta stars, I have cyan stars, and they are just as ugly. So sometimes that works, but in this case, it didn't. Now, maybe I could have got that to work by just playing with the values in SCNR. So by turning it down from 1 to something a little bit lower, maybe through trial and error, I could get something that's a little bit nicer. But I don't know. That's like really, really cyan, and I think that's kind of a lost cause. So I'm going to undo everything I did there. Undo the first invert, undo the SCNR, undo that original invert as well. So we're back where we started. What else can I do? So again, there are different image combination techniques I can use here. So what I'm going to do here is a new strategy. So I'm going to plan on just removing the stars from this image entirely and replacing them with stars that are processed differently. Now, it turns out that there are ways to combine sulfur, oxygen, and hydrogen in such a way that mimics what your eye would see in natural light. We call this synthetic RGB. So I'm going to do that to create another version of this image that's in synthetic RGB. And the stars are probably going to look a little bit better in that one. So I'm going to take the stars from the synthetic RGB image, combine that to the starless version of my SHO Hubble palette image, and that's what I'm going to use at the end of the day. So let's tuck this SHO image away somewhere for now. Now, for synthetic RGB, I don't want to do any sort of linear fit. The way this works is I actually did the math myself once on how much each one of those wavelengths contributes to the RG and B cones in your eyeball and how that actually works out mathematically. So I need to undo that linear fit for that to work. So I applied a linear fit to hydrogen alpha. Let's undo that. Let's also undo the linear fit to sulfur 2. And this is kind of an unconventional thing to do. So you're probably not going to see this on many other tutorials. Now I'm going to use something called pixel math as a process. And I have kind of a saved cheat sheet here for synthetic RGB. So pixel math is a way of combining channels together using whatever mathematical expressions you can dream up. And I dreamt this one up. So to actually approximate what your eyes would see from a narrowband image, I know that if I take 41% of the O3 data and combine it with 10% of the hydrogen alpha data and call that red, I'm just renaming these identifiers to what I actually called them here. For green, it's going to be 69.5% of O3 combined with 94% of hydrogen. And for blue, where did sulfur go? Oh, yeah, there's back in red. Sorry, I had green selected before. Sorry for the confusion there. So red is actually 50% hydrogen and 50% sulfur. And that was sulfur 2 is what I called it. Green is 69.5% oxygen and 9.4% hydrogen. And blue is going to be 10% hydrogen and 41.1% oxygen. And let's see what happens when I apply that. So I'm going to select one of these channels that are in the expression and click on the square in this case. Again, there's no consistency. And that's going to give me my synthetic RGB image. So let's go ahead and apply the radioactive icon there to pull that out. And it looks green, but I'm going to call this synth RGB. There are ways of correcting that. So don't worry about the green yet. Now, whenever you do kind of wideband image stuff like RGB stuff, it is pretty common to have this green tinge from light pollution. And the easiest way to get rid of it is something called automatic background extraction. So I'm going to use the automatic background extractor process. Again, this is accessible through the process menu. And I'm just going to use the default values here to it and click on the square to apply it. And that will just basically balance the color channels for me automatically. And I'm going to go ahead and hit the radioactive button to reapply a correct stretch to that image. Already, that's looking a lot more natural, right? So that's pretty cool. But again, you want to be critical as you go. So if I zoom in, those star colors look pretty decent, right? Like those are looking pretty realistic. Some of them are whitish, some of them are red, maybe a little bit of blue here and there. That's what stars look like. However, there's kind of a green tinge going on there still, and I don't like green. There's a lot of green noise going on as well. So we used automatic background extractor to rebalance those colors, but there's still kind of this green noise going on. And the easiest way to get rid of green noise is a process called SCNR. Don't ask me what that stands for. I don't remember. But you can see here by default, it's set up to remove green because it's such a common problem in imaging. And all I got to do is select my image, pull up SCNR, and hit the square. No more green. Look at that. So now that greenish star is white like it should be. It's magic. Still pretty noisy though. Let's try and hit that noise a little bit. So again, I'm going to hit Noise Exterminator. We'll go with 75% to be consistent again. All right, cool. So now I have kind of my fake wideband image and my real narrowband image side by side here. And my strategy again is to take the nebula from this one and combine it with the stars from this one. But first, I need to stretch these images. And again, what we're going to be doing is taking these from the linear domain to the nonlinear domain and kind of approximating what we're seeing visually here, but actually applying that stretch to pull out that nebulosity for real to the actual image data. Now, there are a million ways to do this. And again, this is kind of like a really deep rabbit hole you can go into. Once you get to that diminishing returns point where you really want to squeeze that last bit of quality out of your images, there are techniques for kind of like stretching different parts of the image differently. I'm not going to go there though. I'm going to keep it simple for you. So the easiest way to do this is to use histogram transformation. And again, the UI is terrible. So let's say that I'm pretty happy with how that looks. It's at least a good starting point. So let's just do that. Let's apply that for real to the image. To do that, again, I'm going to hit that radioactive icon just to make sure that I'm applying the function that I want. And I'm going to go ahead and, well, first, let's be critical a little bit here, right? So do those stars still look good to me? Yeah, I think they're all right. I think they're all right. They're good enough to start with at least. So to do this, the UI for this is just laughable. I'm going to take the triangle icon from my screen transfer function and drag that to the bottom bar of histogram transformation. This makes zero sense, but this is how you do it. And what I've done is applied that screen transfer function to this histogram transformation process. Now, making sure that synth RGB is selected, I'm going to click on this square icon to actually apply that transformation, and it turned the screen white. That's because I'm currently applying a stretch on top of my stretch, so everything looks washed out. So I no longer need this screen transfer function because I've applied that transfer for real to the image. So to get rid of that, I'm going to click on this little reset icon here in the corner to not apply that anymore, okay? So now I've applied that stretch to the image for real, and you can see that green bar is gone, indicating that what I'm seeing is what I'm really getting there. Let's do the same thing for SHO. So again, I'm going to apply my screen transfer function. I'm going to drag that using the triangle on screen transfer function to the bottom bar of histogram transformation. Make sure SHO is selected and hit the square on histogram transformation to apply that. That washed everything out because I'm now stretching it twice. I'm going to remove the screen transfer function with that little reset icon. And there we are back to where we started. Cool. Yes, PixInsight's UI is terrible, but you get used to it, I promise. All right, at this point, we're done with screen transfer function, and we're done, well, yeah, I think we're done with histogram transformation as well. All right, so we have images we can work with here. So, like I said, our next goal is to get the stars out of this one and only get the stars out of this one, and then put them together somehow. So let's do that next. For that, we use another third-party tool called Star Exterminator. So I'm going to go to Process, Star Exterminator. Where'd it go? Where'd you go? There it is. All right, so for the nebula, I don't want any stars. I just want the nebula. So I'm going to uncheck Generate Star Image because all I want you to do, Star Exterminator, is get rid of the stars. And again, there are things you can set here, but I'm not going to mess with them. Hit the square button to apply that. And while we're waiting for that, a quick note. The reason that I'm doing this after stretching the image is because once you remove stars and play around with it, it can be a little bit harder to find a consistent stretch between the stars and the non-stars image. So by doing that stretch first, it saves me a little bit of thinking. Check that out. That's kind of pretty in its own right, right? Just the starless image of that nebula is kind of cool. And it's magic. Like apart from that little halo there from that really bright star, they're all gone. And it filled it in quite nicely. So that is really, really cool. So for the synth RGB image where I just want the stars, I'm going to do the opposite. For this one, all I wanted the stars. So I'm going to hit generate star image because that's what I want. And make sure that's selected and apply that. All right. And you can see it gave me a new image of just the stars that it extracted from that RGB image. So I'm going to put that synth RGB image away and keep the stars one. I'm going to rename it to just stars. All right. So now, before I combine these, I'm going to process them individually. And that's kind of the main advantage of separating the stars from your image. You can really focus on making the nebula itself look as good as possible, making the stars look as good as possible, and only then putting them back together. So let's do that. So for that, I'm going to use a process called curves transformation. And I'm going to reset this. All right, so let's start with the nebula here. All right, so we can use what's called this preview pane here to actually visualize what the curves I'm applying are going to do in real time. So I'm going to click on this circle, which means real-time preview. And that's going to let me visualize what my settings are doing as I adjust them. So first of all, I want more contrast. So I'm going to make sure this is set to RGBK, meaning that I'm applying this curve to every channel at once. Excuse me. So I'm going to make sort of a contrasty S curve here. I'm going to take this upper quadrant here and drag that up a little bit to brighten up the nebula itself. And then I'm going to go down here to the bottom left quadrant and drag that down a little bit to make the background a little bit darker. And sometimes you want to do this in multiple steps. You know, you don't want to change too much at once if you can help it. But, you know, I don't want to be here all night. So I'm just kind of go with what looks right to my eye. And remember that once you add the stars back in, it's going to add a little bit of a distraction to your eye as well. So you might want to err on the side of being a little bit more contrasty than less. We can always change this more later as well. The main thing, though, you want to be cognizant of is that you're not blowing anything out. So, you know, if I were to stretch this out too much, you know, I'm going to start blowing out details there and things are going to wash out to white. Don't want that for sure. And if I pull things down too much here, I might start to lose detail in the background and lose some of those fainter details of the image. So you want to kind of keep an eye on those fainter regions of the image and make sure that they're not disappearing entirely and kind of make your own artistic call there of what kind of contrast looks good to your eye. I'm pretty happy with that right there. So to apply that, I'm going to hit the square button. And now you can see that I'm applying that curve again. I need to reset that there to not do that. What more do I want to do? There's still kind of a greenish tinge to that. Again, I don't like green. So I'm going to just select the green channel here and just pull that down a little bit. And you can see already it's kind of making the gold look more gold and the blues look a little bit more rich. So let's go with that as well and apply that. Reset again. Another thing I can do is boost the saturation a little bit. You know, it just makes it a little bit more visually appealing, makes it pop more. To do that, I'm going to hit on the S icon here for saturation. And I can grab on the middle of this curve and drag it up a little bit just to increase the color saturation a tad. Let's apply that as well. All right, now I can close out of curves transformation and close out of that preview, and you can say that it did apply that to the image itself. So now I'm happy with how the nebula looks. Let's make sure I'm happy with how the stars look as well. Let's go ahead and zoom in. And again, I'm seeing kind of a green tinge there that I don't like. So I'm just going to address that. So again, I'm going to apply curves. I'm going to reset that. I'm going to set that to RGBK, and I'm going to apply the preview window. And the only thing that I'm really trying to fix here is that green tinge. I'm kind of happy with the shape of the stars. I'm happy with how big they are. I'm happy with how bright they are. If you did want to dim them down a little bit, though, you could just drag that down a little bit here. See what I'm doing there? So if you wanted your stars to be less prominent, you could just do that. But I like how they are. So instead, I just want to get rid of that green. So I'm going to select green again and just pull that down. And you can see already that bright star is a little bit more white and less green. Because stars in the real world are never green, people. It does not happen. Let's apply that. All right. Now, before I combine these, I could make that nebula look a little bit better. Before I do that, though, any questions? Oh. All right, let's finish this puppy up. So one thing I want to do is kind of enhance the contrast of this object here. So it looks pretty cool already, but it could be cooler. I could make those tendrils pop out a little bit more by applying what we call local histogram correction. So to do that, I want to only apply that contrast enhancement to the object itself. I don't want to be doing contrast enhancement to noise or kind of this less visually appealing region of the image here. So I really want to focus any further processing just on this part of the image. And there's a few ways to do that. I could create a circular mask, or I could cheat, which is what I always do. What I'm going to do instead is create what's called a luminance mask that will mask out everything but that part of the image for the most part. To do that, I'm going to go to Process and go to Channel Extraction, if I can find it. And I'm going to select CIE-LAB. That will allow me the option to only extract the luminance channel from that image. Okay, so this is going to take that color image and extract just a black and white luminance channel from it. All right, so that's kind of the black and...
Hey, Frank.
Yeah.
Is that the same as pressing the extract luminance button up on the toolbar?
I imagine it would be, yes. I didn't know that
Okay,
button
I just didn't
existed.
know if the lab color taking the L, if it was the same channel or not.
Oh, it absolutely should be.
Cool.
That's a trick I didn't know about. Thank you. All right, so now we need to make this into a luminance mask somehow. So to do that, I'm going to blow it out. So I'm just going to go back to curves here. Again, reset it, activate the preview window, go to RGBK, and just go nuts. So I'm just going to apply a ridiculous amount of contrast to this, maybe in multiple steps even. And the important thing is to kind of get some brightness around those edges that I want to enhance. Again, there are other ways to do this. I'm just showing you one of the easier ways. All right, so if you look at this, you can see that we're going to be concentrating this process around this image here, this area of the image where most of the detail is. There's going to be a little bit in this part of the nebula as well, which is fine. There's still some interesting detail there as well. But for all these other sort of outside areas, it's not going to do anything, which is kind of our goal. So let's go with that. Now, the problem we have is that it's still kind of noisy. So I don't want to be applying a filter or a mask in a noisy fashion. So I want to blur this out a little bit. So to do that, I'm going to go to Process, Convolution. And what convolution does is make things blurry. So how blurry? That's what the standard deviation slider does. Let's crank that up, around 4 or so. And apply that to our luminance mask. And you can see that just blurred things out a little bit to get that noise gone. So now I'm going to rename this to luminance mask or lum_mask, just so I don't forget what it's for. And now I can apply that to this SHO image to restrict my further processing to the region defined by that luminance mask. So let's go ahead and drag that. Again, the UI is terrible. We're going to drag this tab over here, and it has to be very carefully placed into the left-hand area of this image. And you can see that what we end up with is this red region where things are masked out. The things that are not red is where our processing is going to be applied. So it looks reasonable. However, that's ugly. So I'm going to right-click on this and go to mask and say, I don't want to show the mask. But you can see that it's still got this kind of like a brown color to the tab, indicating that there is a mask applied, in case you forgot. Now, what am I going to do? Well, I'm going to apply something called local histogram equalization, which is basically local contrast enhancement. All right. Now, this is another case where you need to experiment because less is more. If you apply too much of this, it's going to look weird. And just to prove my point, I'm going to go with the default arguments here where the amount is 1.0. Make sure that's applied, my mask is applied, and we're going to hit the square and see what it does. And that looks different, right? So you can see that really enhanced the contrast within objects within that object. It really made things pop, but it looks a little bit unnatural. Like I think we went too far. So again, you got to be critical as you go and kind of like say, I went too far. Like, don't be afraid to correct yourself and try different things. So I'm going to undo that. And instead knock this amount from 1.0 down to like 0.25. Less is more when it comes to processing. You really want to preserve what's really in that image as much as possible. All right, so I think that's a much more natural looking result. I have enhanced the contrast a bit, but it doesn't look goofy. So I like that. And again, I'm kind of using that Herbig Harrow object there as kind of my metric as I go along. It's still nice and visible and you can see what's going on there. So I'm pretty happy with that now. Let's go ahead and remove that mask by right-clicking on it, going to Mask, and saying Remove Mask. All right. And we're done with that. Boy, we're almost done, I think. So now we have our SHO nebula image that we're happy with. We have our stars that we're happy with somewhere. There they are. Let's put them together. So to do that, I'm going to use a process or a script rather called blend. So under script and under utilities, there's something called blend. And I think this is actually a third-party one. I'll have to look that up. If so, I'll send a note as to where to get that later on. Yeah. This is actually from Hartmut Bornemann. So this is part of an add-on as well. So you want to get that too. Makes life a lot easier. But the way it works is it lets you combine these images in a way that makes sense visually. So we need to select a lower image and an upper image and how to blend them. So the lower image is going to be the nebula. So for the lower image, I'm going to select SHO. For the upper image, I'm going to select my stars. And for the overlay mode, I'm going to use screen, negative multiply. For whatever reason, that's what works. And then hit ready when I'm done. And there we have it. So there's a bunch of intermediate images here that we can just get rid of. Here is our final combined image. Check it out. Let's call that Pelican. Cool. And at this point, you could do some final tweaks if you want to. Let's say you want to boost the contrast a little bit more. You can just go back to curves. Again, go to the preview window, clear it out. Let's punch it up a little bit more. Apply that. Reset. Maybe boost the saturation a tad more. Apply that. Still seeing a little bit of green. Pull down the green just a tad more. Again, you just got to kind of eyeball it here and do what looks good to you. And I'm pretty happy with that now. Close out that preview window. Here's our final image. But again, the orientation's weird. Last thing I'm going to do is rotate it. And let's try some different rotations. So under process, there's a rotation process. Let's try just 90 degrees. Oh yeah, that's better. I like that. I like that. So from here, you could save this out and like do more tweaks in Photoshop if you wanted to, or just take it as it is. But either way, you got to save what you got, right? So you definitely want to save this project before you lose it. I'm going to save the project as a whole again, just kind of saving over what I had before. That way I can go back and redo things. You'll often find that when you look at this image the next day, you'll say, oh, I wish I did this differently, or I don't like how that looks. And this will make it easier to go back and tweak things further after your brain kind of has a little bit of a reset. And I do recommend, by the way, don't post these to social media until the next day, because inevitably there's going to be something you wake up to at 3 in the morning saying, oh, I wish I did this differently. So we'll just wait for that to write out to disk. There's a lot of information there because it's writing out every intermediate file that we changed as we went as well. that can add up. All right. And finally, to save the final image to disk, we can go to File, Save As. And you can save that in PixInsight's own native format, XISF. You can save that as a PNG or a JPEG for social media. Or if you want to do further tweaks in Photoshop, you could save it as a TIFF rather. Let's call that Pelican 2 or something. And when you're saving as a TIFF, however, make sure to change that from 32-bit to 16-bit unsigned integer. Otherwise, Photoshop doesn't know what to do with it. So now I have a TIFF file saved off that Photoshop can use. And again, I can make a PNG or a JPEG as well. And we're done. That's it, folks. Pretty cool, huh? There's the Pelican Nebula process from beginning to end. Any questions or problems or doubts or anything like that before we close up?
Yeah, I have a question.
Sure.
What would change if you have a color camera? I mean, can you still achieve similar results using a color camera and the L Extreme filter that's optolong?
Yes. I'm hoping to bring John Starr on for another workshop specifically on that. The short answer is yes. Most of the stuff that we looked at can be done in that workflow as well. So I think there's a couple of ways to do it. And Wes, if you know anything about this, feel free to chime in. But you could just process that as a normal RGB image because it is an RGB image. It just has all the light pollution filtered out for you. Or you could try to extract the individual RGB channels from that image and treat them like narrowband channels. So in that case, you could treat the red channel as hydrogen and sulfur combined, and you could treat blue as oxygen potentially, and just pretend, right?
That probably makes it complicated. I did this for the Horsehead Nebula, and it comes. I mean, there's a lot of detail, but it's mostly red because that's the color coming through the filter, predominantly the hydrogen. And I was just wondering if there's any way. I mean, there's different colors out there, oxygen, maybe sulfur. I don't know. And I'm just wondering, what I can do to make it better. At the moment, it just doesn't look natural.
Yeah, I mean, the Horsehead is an example of where you kind of want to do your research because it is mostly hydrogen. You're not going to see a lot of oxygen or sulfur in that object, it turns out. So the best way to process the Horsehead and that whole region of Orion is just by enhancing an RGB image with hydrogen alpha. So, my recommended workflow there would be to just capture it like a normal galaxy or RGB wideband image, and then hit that with narrowband image and combine the two together. And again, that's an entirely different workflow. There are scripts for that though. That makes it easy.
Okay.
But yeah, every object is different though. For the Horsehead, you're not going to get any of that oxygen stuff.
That's what I thought, but the nebulosity, what do you call it? Nebula next to the big star on the other side.
Yeah, there's a reflection nebula.
There's more color and more contrast associated with that, and
yeah, that's a good thing to talk about because that's actually a reflection nebula. Let me see if I can pull up a Horsehead picture here.
I mean, everything just all red the way I have it now, and I do process with PixInsight, but you went through a lot of additional steps that I usually don't go through.
Right. I don't remember which one's the good one here. I have a lot of Horsehead colors. That's not that one. This is one of my very early attempts at the Horsehead, but there's that nebulosity you're talking about there, that blue stuff there.
Yeah, and over to the left too, on my left. That all looks pretty good. Mine looks too red, and even the black region shows up as red. There's hydrogen there, and it's just coming through.
Yeah, with really long exposures, you can see what's going on there. That's actually not the best image I have. But the point I wanted to make, though, is that blue region below the Horsehead is actually what we call a reflection nebula.
Okay.
So that is not an emission nebula that's being ionized oxygen or whatever. It's just a reflection of a star off of gas there.
Okay.
So for that, a narrowband filter doesn't actually do much good. You're better off with RGB imaging for that.
Okay.
So again, you just kind of have to do a little bit of homework ahead of time to understand the best way to process some of these things.
Yeah.
And of course, I can't find the one that's really good,
Of
but take my
course.
word for it. Cool. Good question, though. But yeah, stay tuned. I'm hoping John Starr can do a workshop specifically for one-shot color cameras with narrowband filters because it is slightly different.
Those dual band filters, the HA can be split apart easily enough because HA is all fine on the red, but the O3 is, like you said in the beginning, it's a little bit it's mostly in the blue, but a little bit in the green too.
Right.
So there are scripts that will tear that apart and put it on a proper O3 channel. The split between the green and the blue.
There are scripts that will automatically do that.
I believe so. It's probably using pixel math to take a little bit of each one.
Yep.
Yeah. Sounds like a lot of extra work.
That's what this hobby is.
Absolutely. That's the fun part. Cool. All right. Anything else? Hey, it's 8:30 exactly. How about that? How to do that? Hour and a half, just as promised. But if there's any more questions, I'm happy to take them.
Hey Frank, when you was that CUDA you installed, the CUDA scripts that allowed you to have some of those things run on your graphics card?
Yeah. So my day job is working as a developer that does a lot of stuff with CUDA and AI and stuff. So I had that stuff set up already. But yeah, if you go to the RC Astro website, they have a whole page on how to set things up just so that their plugins will see it. You got to
I
install.
was very jealous of how fast that ran on your
Yes.
computer.
Well, if you do have an NVIDIA card, it can be done. You just need to install CUDA and CUDNN and put the right DLLs in the right place, basically. So if you're at all computer savvy, it's not that tough and well worth
Nice.
doing. Because yeah, it's way faster. Cool. All right, folks. Well, I will be posting a recording of this on our YouTube channel tomorrow sometime, hopefully, if life doesn't get in the way. But thanks so much for participating tonight. And again, if you're watching this on YouTube after the fact and you want to learn more about our organization, head to cfas.org to learn more and maybe sign up. Thanks, everyone. Good night.